correlation coefficient R, which is connected with this coefficient in this equation, and at the beginning they have identical space structure. So this imaginary part disappears, and at the beginning everything is the same. Also, this is a result which has already been presented today in the morning. Correlation coefficient is some value which is connected with dispersions of two values A and B, and product of these two dispersions depends on this correlation coefficient, and uncertainty relation for these two values, for example, momentum and coordinate, depends on this correlation coefficient, and this product is much greater, can be much greater than in the case of uncorrelated packet in G types, where G is the coefficient of correlation efficiency. The greater this coefficient, the greater is the product of these two values. And we have correlated packet. This correlated packet moves in space and time. It is easy, it is possible to find wave function for correlated wave packet. To find these wave functions, we can do the same as we have already done for uncorrelated wave packet. We can write a relation which is connected with the amplitudes of Fourier components, of amplitudes of plane waves. We can find a component for this plane wave in every state. For correlated packets, wave functions can be calculated. We can find it. We can use this expression, the amplitude of every component, Fourier component of every plane wave, in this equation. We can find this integral. This is component, this is integral, this is total wave function of correlated wave packet. And we can find, it is a little bit great, an equation which describes correlated wave packet. So we can analyze this equation, and we can analyze the behavior of this packet during its motion. What is the main? The main idea is, as I've already told you, that during its motion it is not only spreading in space and decreasing in amplitude. Its evolution is much more complicated. Not here. From the analysis of this expression follows that during the motion of correlated packet, evolution of its structure is more complicated. It differs correlated packet evolution from the monotonous spreading of uncorrelated packet. We can make analysis and we can see that at the beginning these packets have the same form. But during its motion, the amplitude of correlated packet decreases greatly at some place. And later it is returning to the initial position. And after some time, correlated packet becomes even wider than a correlated one. So we can see that in a specific place, this place can be calculated if we know parameters of this packet. A collapse of wave function of a correlated wave packet takes place. It can be seen, this is the result of calculation, and it can be seen, this is some kind of diagram, that we have initial wave packet, we have some collapse, and we have decrease of wave function. Also, this result is presented on this figure. So with time increase, for uncorrelated wave packet, we have only spreading of size and decreasing of amplitude. When we have correlated wave packet, we have increase of amplitude in some place, which means collapse of packet in some place in space and time. And after this collapse, its amplitude decreases greatly. This is the result of calculation. This is density plot, which describes the amplitude of correlated wave packet on space and time. And we can see that really this collapse takes place in one point of space and time. Before we have white packet, then we have collapse, and then its amplitude increases and it becomes white. It is possible to use this point, this dot, for different purposes. We can calculate the amplitude of this wave packet. We can calculate how it depends on time. We can calculate the time which is needed to make such collapse. If we know this time, we can find the minimum width of this packet. And this width is g times less than the initial width of the packet. If we have g equal to 10 power 4, 10 power 5, then we have a great decrease, a great squaring of this packet. And after the collapse, the width is increasing in g times, so we have squaring and spreading. We can compare it with uncorrelated wave packet, where there is no such coefficient. And the same for amplitude of this wave packet. We can calculate, if we know time of collapse, distance where collapse occurs. If we know this distance, we can calculate wave function, and we can show that wave function in this place is g times greater than the initial wave function. So beam is collapsing in one point and then squaring. And we can show that after this collapse, the amplitude is decreasing very fast. We can also find average value of momentum and momentum dispersion, and we can show that the amplitude of energy fluctuation is g times greater than this value, g times square greater, which means at this point we have a great increase of uncertainty of energy. In this place where we have collapse, if this packet is correlated, the uncertainty of energy allows us to receive at one point energy which can be thousands, hundreds times greater than the energy that this particle has. Uncertainty is thousands times greater than the energy. So, for example, if we have uncorrelated proton, the width of this, if we represent a correlated proton as wave packet, the width of this packet is nearly 1 angstrom. For example, we have low energy, uncertainty of this proton in uncorrelated state in 10 power minus 3 electron volt. If we have correlation coefficient of correlation efficiency 10 power 4, that we have uncertainty of energy 100 kilo electron volts, which means that for one moment this proton can receive very great energy, and it can be used for the purposes of reactions. This proton has low energy, but uncertainty of its energy allows us to use it in nuclear reactions. And we don't need acceleration to receive great energy. Such energy exceeds the average energy of proton longitudinal slow motion in low energy nuclear reactions experiments, where average energy can be equal to several units or tenths of electron volts. So, proposed scheme, how it is possible to use it, we can compare with traditional scheme. Traditional scheme, what we have? We have beam source. Beam source is generating low energy particle beam, uncorrelated. Then we have some accelerator. Accelerator is a great facility. In this accelerator, these particles are accelerated. We have high energy particle beams, uncorrelated. They interact with target, and we have some nuclear reactions. In our case, we have same beam source. We have the same low energy particle beam uncorrelated. But we do not need great accelerator. We can't build accelerator in our small laboratory. We need system of correlation formation, where correlated packets are formed. After this system, we have the same low energy particles beams, but they are correlated. They are moving towards the target, and they are interacting with this target only in a small layer after the T collapse, after the formation, on the distance x collapse from this distance. On this distance, in this moment of time, we have a great correlation coefficient, we have a great decrease of energy uncertainty, and we have possibility of energy release and low energy nuclear reactions. For example, if at the beginning we have 0 coefficient of correlation and equal to 1 coefficient of correlation efficiency, if in this place it is much greater than 1, then the energy, uncertainty of energy can be much greater than it was at the beginning, and we have collapse, and we have great energy release, and we have a possibility to create energy reactions. This system, this action occurs only in this thin layer. It doesn't occur there, and it doesn't occur there. So we have to built our system very precisely. So how it is possible to build such correlated packets? The main idea, it was already presented today, is modulation of parameters of a quantized system within which the particle is located gives us a possibility to make such correlation. For example, we can have a quantum oscillator, and we can modulate this quantum oscillator. And during this modulation, the correlation between wave functions in different states appear, and this correlation allows us to create coefficient of correlation and to form correlated wave packet. During such modulation, phase correlations between wave functions in different states appear, and this system can be of different nature. It can be a real field of some quantum system. For example, it can be a field of crystal in which a channeling particle is moving. It can be a field of some magnets, and interaction of magnetic field with charged particle also allows us to create such system. It can be any system that is suitable for these purposes. It can be some dynamic structures, nanopracks, and etc. So, for example, some systems that we want to propose. First system is a system of magnets. For example, if we have some particle, which means proton beam, and this proton moves in the system of magnets which are oriented in such a way that magnetic field changes, we have an amplitude, we have an oscillation of this charged particle in magnetic field. We can find the frequency of this oscillation. It depends on the amplitude, reached amplitude of this field. And if we know this frequency, we know that the frequency of the interaction is modulated. In some places the field is great, in some places there is no field, so we have some modulation of this frequency. We have some changing frequency of oscillator with changing frequency, and in this case it is possible to form correlated state, and it is possible to form a correlated packet. In the case of free packet motion, such state can be formed during a periodically inhomogeneous perpendicular magnetic field. We can calculate parameters that we need. We can take typical magnets. Typical magnets have a field of nearly 10 kiloarstud. If we take such field, we can calculate the frequency which is connected only with this field and with the nature of the particle which we are using, for example, proton. We calculate this frequency. This frequency depends on this amplitude. If we take, for example, such parameters, we can take some velocity of a particle, we show that this system would be optimal for protons with energy of several kiloelectron volts. And unfortunately, this system has some lags. For example, in our article that was published in Journal of Experimental Theoretical Physics, it was shown that such modulation is not very effective. During such modulation, we have an increase of parameter of correlation, but also in such system we have an increase of amplitude. So we are not only forming correlated state, but we are also giving energy from our system to our oscillator. It's some kind of accelerator. It is not very good, and the maximum coefficient of correlation, which, as it was shown, can be made in such system, is nearly 0.98. It is not so great. The coefficient of correlation efficiency is only 5. We need greater. For our purposes, we need coefficient of correlation efficiency 10 power 4, 10 power 5 to make a really great uncertainty of energy for our reactions. So it is much better not to use such system with such way of change of frequency, but to modify it and to use a small modulations of frequency when we have some constant frequency and this frequency changes with some small coefficient. It can be an oscillator with changing amplitude or with changing width. Both ways allows us to create correlated packets. And it was shown in our previous articles that in this case we have a very fast increase of correlation coefficient, but only on several frequencies. We can show that if frequency of modulation is equal to the frequency of oscillator, we have a great increase of correlation coefficient, and during several periods it has a value 0.999 or even 0.9998, depending on time. Depending on different coefficients of modulation depths. And it was shown that for such system, the greatest efficiency is when frequency of modulation is either equal to the frequency of oscillator or 2 times greater. This is the dependence of averaged correlation coefficient on frequency of modulation. On other frequencies, effect of correlation formation does not occur. And so we need such type of modulation. I have 3 minutes. We know that the optimal value of modulation is in the case when the modulating frequency is 2 times greater than the frequency inside this oscillator. And we propose to use periodically changing magnetic field. For example, we can use a coil, and parameters of this coil are modulated with modulation parameter G. For example, during its motion, in some places this field is greater, in some places this field is smaller. We have motion longitudinal, we have motion perpendicular. This perpendicular motion is quantized, and we have oscillator in perpendicular direction. We have quantized states with some wave function, with some momentum and some energy. We have modulation of field. This modulation of field, for example, let's take field the same as it was in the case of standard magnets, for example 10 power 4 Earth. If we know this field, we can calculate the frequency, 10 power 8 seconds minus 1. If we know this frequency, if we take protons with energy 200 electron volts, we can calculate their speed. If we know this speed, and we can calculate the distance which is needed, the period of this coil, and we can find this period, the frequency of this oscillation with this coil has to be 2 times greater than the frequency of oscillations. And we can easily find that the period of this coil for such parameters has to be nearly 1 centimeter. Of course, if we change the magnitude, if we change the amplitude of our field, we can change these parameters. And it was shown that for formation of great coefficient of correlation that is equal to 10 power 4, 10 power 5, we need omega t is equal to 50-60. It is formed here, not at the beginning, but after some time. After some time means that on some distance. And the number of periods which is enough for formation of such system shows us that the length of this coil has to be nearly 1 meter. So the parameters are quite realistic. That is not something fantastic. Amplitude of field, period, length of our coil. My time is ended, so I want to go to conclusion. Conclusion. Considered above features of the correlated wave packet make it possible to predict the possibility of its use for a number of applied and fundamental problems. Along with the collapse on a specific distance, the creation of such a packet is accompanied by a significant increase of its kinetic energy fluctuations, which can be many orders of magnitude higher than the average motion energy of the packet itself. It may allow to use them for nuclear reactions even at low particle energies. The importance of correlated states and their fundamental difference from uncorrelated superpositional states is the following. Such states may have great fluctuations of energy that can exist for a long time without violating the law of conservation of energy. Thank you.
Now we'll have some questions.
How are we going to comment this actually Gauss time and Gauss point in terms of the magnetic is going to increase intensity of this magnetic field at the point of the chords, at the time of the chords, or not?
We have not calculated speed of a particle.
Microphone.
We haven't calculated the influence of spin on these processes, so I can't answer your question. But I don't think that it would influence in some way.
No influence.
I don't think so. Spin of proton is small enough, and magnetic field is not so strong. No questions.
I have a question. I'm not a theoretician, so I have a hard time following all the calculations. But physically speaking, are you talking about a large number of deuterium atoms or something like that? What's happening physically?
This formalism can be applied either for one particle or for a whole packet of particles. There is no difference which particles we are talking about. I was talking about proton as an example. We can take about proton, we can check about deuterium or any other particle. It doesn't matter. The parameters of our system, of course, changes, but this change is not something that affects the main conclusions. So this formalism can be applied for any types of particles.
So if I imagine a capacitor, with many particles inside, and I put a pulse with a drifting frequency, may I get something?
Changing frequency of capacitor and motion of particles inside this capacitor. I think yes, because capacitor, if capacitor changes, if capacity changes, the energy changes. If energy changes, we have some oscillations of parameters of oscillator, and their coefficient of correlation may change. So I proposed only some types of possible valorization, but other types are also possible. I don't think that it is something principal.
May I? So this effect works also for electrons?
Yes, of course, this effect works and for
And my stupid question, why nobody tried to use for the usual particle accelerator we have a lot of dissipation, Bremsstrahlung and so on. So I cannot imagine. Your idea seems wonderful. Why nobody think about to apply?
I can't.
Because Bremsstrahlung emission of electrons is the most dangerous, most problematic to have electron beams that is extremely useful. So maybe you can propose. So it seems too much nice to be true.
too much nice to be true. Unfortunately, I can't answer why nobody has made it, but we have proposed. I think that's a simple enough idea, so it is possible to check it, to take some real parameters and to check for electrons.
But you make some small experiment, some beginning experiment, or just idea?
No, we have no experiments. That is a new result. We haven't checked it. That is the question for future.
So, okay. I hope it's really well questioned.
I think it's the last.
The last.
Stop the question. And upload.
Okay, thank you.